So it's a broadband process. You excite at one wavelength, you get a broad emission somewhere else. Okay. And as opposed to the absorption process we talked about before, that Colin went through, you don't have to have the light coming in match an absorption line to have it excited to there. And then so the light in Rayleigh scattering, what we've talked about before so far, light comes in. You can think of it as light coming in, the scattering process, light coming in and then going out at the same wavelength. And you have this virtual state in the middle. It's not a real absorption point, it's just a virtual state. It's sort of cool. These virtual states can occur as long as, by the uncertainty principle, Heisenberg's uncertainty principle, these virtual states can occur as long as the energy times the time that they exist is smaller than h bar, okay, Planck's constant. It's pretty cool that these things can happen. So anyway, so Rayleigh scattering you can think of as light coming in at one wavelength, exciting into this virtual state and coming off at the photon coming off at the same wavelength. With Stokes and anti-Stokes scattering, which is Raman scattering, effectively the Stokes scattering, the light comes in, excites this virtual state, and when it's emitted at a slightly different change in a lower energy, which means the photon wavelength is longer. So this is the normal Raman scattering you see. And then anti-Stokes, the light can come in, and when it's emitted, it actually comes off with more energy. So here you've taken energy from the molecule that you've excited. Here you've given energy to the molecule that you've excited. And this is the more probable case. And so this is the one you see most of the time. But you have Stokes and anti-Stokes scattering. So it's sort of cool that it can happen with this virtual state. And by having the virtual state, it means that it can happen throughout the spectrum. If you end up with one of these virtual states being close to a real state, then the Raman scattering is enhanced at that wavelength. And so chemists use Raman scattering to help them learn things about molecules and do identification of molecules.
Question.
Yes?
Anti-Stokes scattering, the initial frequency of the incoming photon, is that relative to something? Because it's higher than all the others? Is it saying it's a little bit excited compared to like a ground state? Or?
I'm not sure why I drove.
Well, the emitted one has to be wider, longer, right?
So in the anti-Stokes scattering, you come in with some wavelength, and when you leave, you've gotten energy from the molecule, and so you come off with a photon that's a higher energy. Okay, and so that's all that I'm trying to show there. So we have that. If you looked closely at that picture of the differential scattering cross-section that I showed before, you can notice it's sort of made up of two humps, two Gaussians, and basically the strength of each of these varies with temperature, and so and it varies with salinity, and so Leonard Caputo and Hogue in the 70s talked about using this with lasers to remotely sense water temperature. So they would have a laser system in a helicopter or whatever flying along and do profiles of water, the temperature profile, using the strength between these two things. Okay, so that's sort of good. And then now this shows the Raman shift in terms of, did I say it right? Anyway, the shift in terms of inverse centimeters, the way you use this is 1 over the final wavelength in centimeters is equal to 1 over the initial wavelength in centimeters minus this shift in inverse centimeters. So that's how you sort of work with that inverse centimeter deal. That makes sense to people, you see? So basically, 1 over the wavelength of the outgoing light is equal to 1 over the wavelength of the incoming light minus the shift, 3400 centimeters to minus 1. Okay, so that's how you work through that number. Okay, so why are we even talking about it here? In the early 80s, we started getting, the oceanotics community started getting multispectral instruments. Before that, we talked about it yesterday, most of the instruments were only at a single wavelength or a very limited number of wavelengths. But then we were either getting full-blown spectrometers. Ray Smith and John Tyler built one at the Viz Lab, or multi-channel radiometers. Biospherics made this MER 1032 that had, I don't know, 11 or 12 channels of upwelling radiance, downwelling irradiance, and upwelling irradiance in it. And when people were doing profiles, what they were seeing is diffuse attenuation coefficients less than water absorption. So they were trying to figure out what was going on. Why I spent, remember we had that picture yesterday of that tank in the middle of the parking lot, the visibility lab? I spent many days out with that tank with this MER 1032 instrument, trying different things, trying to see why it might measure an absorption coefficient less than water, whether there was leakage in it, in the filters, some out-of-band effects, things like that. So everybody's trying to figure out what was going on, why that was occurring. Basically, if you look, here's an example of the diffuse attenuation coefficient for upwelling radiance as a function of wavelength. And the black line is absorption of pure water. And if you measure it in this case, we're measuring between two depths, getting the diffuse attenuation between two depths, either 1 and 5 meters, or 5 and 9 meters, or 1 and 9 meters. Out here, you're measuring diffuse attenuation that's much less than water, which is an example of this problem. People couldn't figure out what was going on down there. And it was most significant where there was not a lot of light in the water column to start with, because of absorption of water was so strong. And so like I said, we were looking for leaks in filters, trying to come up with some reason. Yes?
KL,
diffuse attenuation of upwelling radiance. I should have a little U after it, yeah.
Okay.
So you can have a diffuse attenuation of anything. Upwelling radiance, upwelling or radiance at 70 degrees, whatever you want. So this is upwelling radiance. Okay, so people knew about Raman for laser excitation. It was out, the physics community all knew about it. But we didn't think it was important in the natural light field, and a series of people figured out that we were wrong. If any of us had read the Japanese literature, I was working with it, trying to figure out what was going on in 85 or 86. This paper came out in 84, but most of the people in the US didn't really know about it until Staben and Weidemann and Marshall and Smith were doing experiments toward the 88, and in 90 is when they realized through calculations and such that the Raman would be strong enough to influence the light field. Another sidelight here. You listen to your advisor. My advisor, I'll talk tomorrow about the stuff I did in graduate school, but it was polarized light scattering. My advisor wanted me to make measurements of Raman scattering in the lab with my instrument, and since I could barely see pure water, clean water as it was, I thought it was sort of ridiculous to even try it. I should have been trying it. I could have been ahead of these guys by a couple years, which would have been fun, but I sort of said, yes, Ed, I'll try to work on it, and didn't have time. So listen to your advisor. Okay, so especially if you have a really good one. Me, I don't know, but listen to Ed Fry if he's your advisor. Characteristics of Raman scattering, it's relatively weak. If you look, the scattering coefficient for Raman scattering, the total, is about an order of magnitude less than it is for the elastic scattering of in water, pure water. The scattering phase function is a lot like Rayleigh scattering in water. There's a slightly higher depolarization ratio. So basically it's not an isotropic scattering. It scatters as you've been told how Rayleigh scattering works. The wavelength shift, as I've shown, is about 3,400 inverse centimeters. The strength varies with wavelength at about the wavelength of -5, but that depends on which wavelength you're talking about. If you talk about the excitation, or whether you're talking about how it's varying with the emission wavelength, and one is lambda to the -5, the other is lambda to the -4, and whether you talk about photons versus energy. So it's on the order of lambda to the -5, lambda to the -4, regardless of which one you do. What's that? Oh, I'm sorry. What's what? B sub r, the Raman scattering coefficient. Okay, so the Raman scattering coefficient at 532 nanometers is an order of magnitude less than that of the Rayleigh scattering, which is the one we've been talking about. Okay. This is the best class out of the ones I've done for asking questions. It's really, you guys are really good at it, so thank you.
Ask you what every symbol I don't recognize.
That's perfect. That's perfect. Yeah. No, you guys are really good at it. It's great. Okay. Just say how much the energy shift is in wavelengths. Because it's a constant energy, it's going to shift how much the wavelength changes. So at 400 nanometers excitation, the wavelength shift is about 50 nanometers or so. As you get to longer wavelength, which means the energy of the photon is less, the shift gets bigger and bigger. Okay, but in, say, at 500, the shift looks like it's about 100 nanometers. At 600, it's up to about 150 nanometers. Okay, so yeah.
So this final,
Yeah.
the wavelength equation is like a pretty fundamental equation for what we're talking about here.
Yeah. So this is sort of how to figure out what the emission wavelength is, given an incident
And
wavelength.
that would apply to any kind of inelastic scattering. Is what makes it specific to Raman scattering
The 3,400
Okay,
inverse.
but-
And well, not all. I mean, inelastic processes. This process occurs, and it has a constant energy shift. Okay. Other inelastic processes won't have necessarily a constant energy shift.
Right, but so at least the left-hand side and the whole reciprocal wavelength thing is characteristic of.
That's how you use these inverse centimeter units.
All right.
Is doing something like that,
Thanks.
which is hard to. Yes, ma'am. Maybe if either you guys are better asking questions, or I'm getting more confusing as I'm getting older, which either way works.
Does that mean that the excitation can happen at any point?
Yeah,
Any
yeah,
wavelength?
yeah. So it happens throughout the spectrum. You can get these virtual states and do that.
And this constant is for water.
This is
Or
for
is more general?
Raman scattering in water.
In water? Or
In water. No, in water.
Okay.
This is all for water. Like I said, they.
Yeah.
What's that?
This is for pure water.
This is for pure water. If you have other chemicals, they have very strong Raman scattering, and like I said, chemists use Raman scattering to look at structure. I think I don't know what they do with it. So they use it for identification and such of other materials. Okay. So, but this 3,400 inverse centimeters is water, pure water. Okay. So now, why is it important? If you look at the natural light field, This is the downwelling light irradiance. I've showed you this before. This is the upwelling radiance. If you're talking about shifting light from here over to a longer wavelengths, there's a lot of light here in the blue, not as much in the red. So as I shift, have a lot of energy up here that I can have a lot of photons that can be shifted over into this region where there aren't very many photons in the water. And so the Raman can contribute a lot to the natural light field, okay, which is why it becomes important. This is just showing you the irradiance as a function of depth at 1, 10, and 20 meters, how quickly it's going away in the red wavelengths. And so there's a lot of area up here that Raman scattering can fill up. And so it becomes important up there. So Raman is important because it shifts light from where it's abundant in that blue region to where the elastic part would normally not have much light. So it can shift from where there are a lot of photons to where there are very few photons. And so you really need to be careful when you interpret measurements at these other wavelengths, in the red wavelengths, because your measurements in the field can become influenced by the Raman scattering. This is an example that Howard calculated, showing you the fraction of the light that's, you probably, can you see this? Probably not. So this is a fraction of light, so it's going between 10% to 25% of the light is due to, in the upwelling irradiance, is due to Raman generated light. This wavelength's at 475 or so nanometers, going out to 750 nanometers. So you can see once you get above, what kind of water was this? This is pure water, pure seawater. So it can be, even in pure seawater, even as low as 475 nanometers, it can be a large fraction of the upwelling irradiance. And if you look, this is upwelling radiance, and it's in pure water. It's occurring too at around 475 nanometers and such. Okay, so even for pure water, it can be a large fraction of the upwelling light field. Yes.
We've been doing like filtering and all that kind of stuff. How do you get pure seawater? That's natural seawater? So
the way Howard did it was that he had a computer and he put in the parameters for pure seawater, and out of his Monte Carlo code, it gave him pure seawater results. That's the easiest way to get pure water.
So the fractions that were computed, is that for the total upwelling irradiance or for each wavelength?
So this
for
is,
example, is a red signal, could it be way lower and it's just a high fraction of it in Raman scattering?
yes, this is relative. So at 600 nanometers, 25% roughly of the light upwelling irradiance is Raman generated at that wavelength. Yeah, so the spectrum obviously is going down like this tremendously. No, okay, yeah. Of what? Salinity? Salinity changes the ratio. I mean, in terms of this, nothing. Salinity would change the ratio between those two peaks that the Raman sort of has that shoulder. So one gets stronger relative to the other. So you can, it's a combination of temperature and salinity that changes those relative peaks. And Colin talked about it comes from the structure of how the water molecules bind to each other and sort of the crystals of water that get formed because they get more attached. And at higher temperatures, they're more disassociated than at lower temperatures. Okay. Yes.
Is theta 0?
Okay, that's the solar zenith angle.
That's solar zenith.
Yeah, so it didn't really vary much with solar zenith angle.
You said there's no, I mean, when you actually said there's no salinity effect, but you just showed us a figure from somebody's paper where there's some effect. It's not an important effect, the salinity.
Did I say it was no salinity effect?
No, you said it wasn't very important.
It wasn't important in terms of this. What it does is it changes the shift that it changes the relative magnitude of this peak versus that peak, but it doesn't. Yeah, and so that's the ratio of these two peaks. So it doesn't change the overall Raman scattering coefficient very significantly. It's just changing how much is going into one shift versus the other shift. So, okay. So in terms of this stuff, it's not really a big deal. Here's looking as a function of chlorophyll and with wavelength. And so let's see if we can figure out why that would occur. Okay, so this is the Raman fraction of upwelling radiance, of water leaving radiance, normalized water leaving radiance, as a function of chlorophyll. So very clear water, okay, low chlorophyll, we have a very high fraction at 595 nanometers. And as you increase the chlorophyll, you decrease the fraction of Raman scattering at 595. Why would we do that? Why would that occur from what you know so far? Yeah, so we'll just look at the triangles here because that's the biggest effect. So it starts out with a very high fraction in clear water, low chlorophyll, and as we increase the chlorophyll, the fraction of Raman scattering at 595, that's scattered into 595 nanometers, decreases as you get more chlorophyll. Because the what?
The signal's higher, your water leaving radiance, so your Raman contribution is smaller.
You have more scattering, like
Okay. Absorption. What absorption?
Because there is less noise
Where?
in the rest of the water.
In the whole, all of the water?
Because the phytoplankton are green.
Because the phytoplankton are green?
They absorb, right?
Oh, well, wait a second. Wait a second.
Wait, no, sorry.
When something's green, is it because of...
That's not nice to say. No,
Yeah, that's a wrong thing to say at this point, a week into the class. So as you get more chlorophyll, okay, the water turns what color? From really blue to green. Okay, and it's turning green. Why? What's happened to the blue light? It's been absorbed. It's no longer there. At 595 nanometers, it has been shifted from somewhere in the blue-green over to that wavelength. And so what you're seeing there is as the chlorophyll increases, you have less light available in the excitation band to be shifted over into the other band. Because it excites in the blue. And so the more light there is in the blue, the more that can be shifted into the red. Okay, and so if the light's not there in the blue, it's not available to be shifted.
But didn't we say that it can excite in any wavelength?
It can excite in any wavelength, but the wavelength shift, let's see, here's the graph. The wavelength shift. So if I want to look at 595 emission, okay, it's the back graph, it's sort of backwards. Let's see, at 600 nanometer excitation, it gets shifted by 120 nanometers. At 500 nanometer excitation, it's shifted by 100. Okay, so 595 is probably coming from 500 nanometers. Okay, the light excited at 500 nanometers. Yeah, if you look back at this graph, get one that's in wavelength there. This was excited at one wavelength. And it's broadband, but it's not that broadband. It's 30 nanometers or something, almost the full thing. So it can occur at all wavelengths, but at one wavelength, it's only shifted to a certain band over here. Yeah.
I think I'm a bit confused between
Sure.
scattering and fluorescence. Like
Okay.
when you're saying that there's excitation of one wavelength like blue and then it shifts to the red,
Mm-hmm.
then we also have these kind of things.
You also have that thing, and the difference between Raman inelastic scattering, that the way I'm going to talk about it, and fluorescence is a lifetime of the process. Fluorescence is a very relatively long time frame that the photon's absorbed. There's things going on inside the cell which I don't understand, and then it fluoresces later. It re-emits that light at a different wavelength, and it's used the difference in energy inside the molecule. Okay, versus this is inelastic scattering, the way I'm talking about it here, is a very, very quick process. The photon comes in, almost immediately the shifted photon comes out.
The level of energy in these two processes are the same, or it's just a matter of time, or?
Well, there's a bunch of differences between this and the fluorescence that Colin will talk about in a bit. One is the lifetime of the fluorescence process. In fact, I'm going to talk about that in a second. But the lifetime is much longer for a fluorescence process than for the Raman process. Secondly, because you're using these virtual states, it can occur. I don't have to have this match with a real absorption level in some molecule in this or with pure water. So it can occur at any wavelength in the spectrum. You can get this shift, versus we've already found out for fluorescence, for phytoplankton, they absorb at certain wavelengths, and then they'll fluoresce at certain wavelengths. It's not like at 550 nanometers I can excite the chlorophyll molecule and have it fluoresce at some constant energy shift. That right? Yeah. Okay, so that's one way to separate the two things. What was I? Okay, so we understand this. You got to have light available to be scattered, and so I should say this modeling was all done as Kurt's described. This was done in '99. Even now, we don't know a lot about what's going on in the UV. And remember, we're shifting light from the blue to the red. So these wavelengths at 443 being shifted from closer to the UV, we don't. A grain of salt. So how do you measure it? In the lab, 90-degree scattering experiments. You're trying to get so you light coming in and you look at 90 degrees to see the scattering. The reason is that you avoid forward scattering of elastic processes, or mostly forward. But you have to be really careful to exclude the excitation, because it is a very weak process. So you're going to get more scattering, elastic scattering, than you are the inelastic scattering. So you have to have really good filters on your system. The other thing, we're going to talk about polarization tomorrow, but in general, whenever you have a diffraction grating or these systems, it's disappeared. Colin's excitation emission spectrometer disappeared.
I had to move it into the other lab.
Okay. Well.
You have to use a computer Windows 95.
Oh.
Turns out, and there's one.
Oh, okay. Well, there is one. That's good. Yeah. Okay, so the excitation emission spectrometers are really cool things. You have a they measure for every excitation wavelength where the emission is, and you sweep through this. The thing is there's typically a grating of some sort, or a prism, something to disperse the light on the input, and there's a grating or something on the output to disperse the light on the output. Those dispersive devices are almost always polarization sensitive, meaning that the light coming one way is slightly polarized, and the light coming off will be sensitive to what the polarization is. And as I told you earlier, Raman scattering is polarized. Okay, so if you just take your excitation emission spectrometer and just try to measure Raman scattering cross sections as a function of wavelength, you're going to get screwed up because of this polarization sensitive. In fact, there was a paper that fortunately that was caught earlier in the process because they were going to have some really weird results in there. I tried to do it with a friend's excitation emission spectrometer and realized that this was happening, and so I had to put polarizers in both sides, so I maintained the same polarization state to look at this. Anyway, so you had to be careful with it. The neat thing is if you could get, and I've been talking to Colin for I don't know how many years, if you could put polarizers in there, you could use the Raman scattering from the excitation emission spectrometer to sort of calibrate the spectrometer. And I've wanted to do that during the summers when I've been here. Okay, well, we should try to do it this year. It's been years. Yeah, so we should do it. It's been years I've been thinking about it. Yeah.
Why at the filtering this part? I have a basic question. Is how do you distinguish the Raman scattering than the absorption and the re-emit? When you absorb the light, it's change the electric levels of the electrons, and then re-emit to the lower level, re-emit a different wavelengths. How did you? Are those are not supposed to be the same, right?
So the Raman scattering happens with just pure seawater, pure water. It is not dependent on, well, the excitation emission. It's broad. It'll happen at every wavelength, not just specific absorption bands. Okay.
So is there? I mean, are they very like? If you look at the spectrum, you know this is because of Raman scattering. Those are because of.
Probably, I might flip it around. I would probably look and see where the ones are that are specific wavelengths it occurs at, and those would be due to absorption and fluorescence processes. And then what's left over, what's sort of at all wavelengths would be the Raman. Isolate the ones that are just at specific wavelengths is how I would try to separate it. So how would I separate a fluorescence event from the Raman scattering? I mean, the fluorescence events are going to occur because absorption at specific wavelengths. If you stay away from those specific wavelengths, then you could see the background Raman.
So you don't think there will be like overlay?
No, they will overlay. You're going to get, if in the natural light field, in the ocean with phytoplankton and such, in the red wavelengths, you're going to get inelastic and fluorescence effects occurring, and they will overlay.
So
Yes.
Is there a way to like filter it out, or?
Is there a way to, if you look at a band that's not a fluorescent band, then you would only be seeing the Raman process. Right? Fluorescence occurs in certain wavelengths. It's not a fully broadband. Versus, so if you look where there's not a fluorescent peak, then the background is going to be the Raman scattering. Yes? No? Okay, we can move. So how do you measure this? So in the lab, you look with these experiments. In the field, indirectly, you can make measurements of the light field and sort of model how much Raman should be given what the measured excitation field, and that's what the Marshall and Smith paper was doing, and also the Staben and Weidemann papers. Directly, it's sort of cool, the ring effect. If you remember the solar spectrum, should have another graph. Oh, here. The solar spectrum has these really cool features in it, Fraunhofer lines and some of atmospheric bands, but they're basically really nice, sharp features in it. And if you look at higher resolution than this, the features get even tighter and there's lots more to work with. And the Raman scattering cross-section, differential cross-section, is pretty wide. It's about 30 nanometers or so. So what's going to happen when light's scattered from here over to here is inelastically it is going to fill basically over a large area, a large region of the spectrum, versus elastic scattering would maintain the same shape as this. Okay, so by looking at how the line shapes of these Fraunhofer lines change with depth in the water, you can basically separate the inelastic process versus the elastic. And so that's called, it turns out, I didn't know it to start with, there are like three groups. Oops, I went past, where am I? So there were three groups, a group at NOSC, George Cadwar at A&M, Texas A&M, and then I had come up with this idea of using these Fraunhofer lines to look at the Raman scattering in the ocean. I was describing what I wanted to do to another faculty member at the UM physics department. He goes, "Oh, that's the ring effect. Astronomers have been using it for years." I thought, "Oh, really?" I thought it was an original idea. So anyway, basically by measuring the line shape and the change in the line shape, you can separate the elastic from the inelastic scattering. And so it's sort of cool. Actually, people do, and so by doing that, you can both see Raman and you can also see fluorescence. If you're looking at a fluorescence band, you can separate solar stimulated fluorescence from the natural light at that wavelength by looking at this line filling. Here shows an example of downwelling light. You don't see much going on in the downwelling light here. From 0 to 40 meters, you see that the Fraunhofer line here stays pretty much the same shape. In the blue, if you look in the red wavelengths, as you go down from the surface, you get this nice Fraunhofer line at about 656 nanometers. As you go down in the water column, the line is filled, so by 20 meters, you can barely see it. So that's the effect of all this Raman scattering filling in that wavelength. So by measuring these line shapes, you can get an idea of the inelastic processing, or fluorescence if you want. Yeah.
So you said that these are measured through side scattering experiments
In the lab.
because elastic processes are mostly forward scattering.
Right.
Why is that?
So the elastic, if you have particles in the water, remember the volume scattering function for particles is very forward peaked. Okay, so if you're trying to look in the forward direction, some other forward direction, you're going to be swamped by these elastic scattering events. So if we look, volume scattering function started with this, where this is log beta versus theta, something like that. The minimum in the scattering is typically around 90 degrees. Okay, so, but this is a log scale, so there's a huge amount of light scattered at small angles. And so at 90 degrees is fairly small amount of elastic scattering. Okay? And so you'll have a better chance of seeing the Raman scattering there.
When we were talking about volume scattering functions, that was all elastic scattering.
That was all elastic scattering that we were talking about. Until today, all the stuff has been elastic.
And so isn't that more representative of like a larger particle though?
Larger particles, right? Uh-huh.
Okay. So
But it's very hard to clean water to where you get rid of enough of these that you get more of a just Rayleigh background pure water signal.
Okay, thank you.
Okay, so it's really hard to get clean water. Yes, ma'am. This was, where was the spectrum? 46 JGR. This was in relatively clear water. I'm trying to remember where it was. I'm pretty sure it was off of Miami well, actually, wait. I'm sorry, I can't remember where this data was taken from, and I can't even remember exactly. So G was one of my students, and this might have been a modeling exercise with Howard, although the data looks it looks too noisy to be modeled. So it's probably data that we took, and I can't remember whether it was off California or off. I can't remember how clear the water was. It was not very turbid, but it was pretty clear water. I'm sorry. I need to look back. Yeah, it was not really turbid water. It was fairly clear water. It would have been in the ocean off of either California or Miami. And it was clear enough that what's happening here, the absorption here, is dominated by the water at 650 nanometers or so. Okay. Can we figure out, if I was really good on my feet, I could probably tell you what what K at 490 was from this graph, but at 40 meters, it decreased by how much? I'm not going to do it on my feet like this. Okay, you could do it, but not me. Okay, you can also use this ring effect to look at fluorescence, and so this is sort of an interesting graph where I'm looking at the red where you expect fluorescence, and we're looking at the upwelling radiance off of, so basically the radiance coming off, reflected off of this brain coral as a function of time. This is the downwelling irradiance. You see the line, the shape of the spectrum doesn't change over time from the downwelling signal, but you can see in the upwelling signal, you did get a different shape here. It's sort of interesting. It's the only way to understand it really is is effectively that the fluorescence efficiency is changing over time with this brain coral anyway. So you can see as time went on, we got more fluorescence at that wavelength using this ring effect. They use the ring effect now for, did you have a question that I'm ignoring? Is Monterey Bay? Okay, yeah. So it wasn't like here, but it wasn't like clear either. It was coastal Monterey. Thank you. Now I remember the cruise, but anyway, thank you. So it was coastal green water. What would I want to? Oh, the ring effect. People use this now they've used it from helicopters over crop fields, because by looking at the Fraunhofer lines, they get a measure of the solar stimulated fluorescence from the crop, and you can tell water stress from your crop field. So people used it from helicopters. Now that instruments are getting better and smaller, they're talking about flying drones being able to do it. Just the other day, I started talking to Dale Kiefer, who's a ocean optics person at USC. And he had got contact from somebody at JPL who's looking with very high resolution of remote sensing data over the ocean. And they're talking about using this ring effect too, and the signals that they see they're taking a land instrument and then applying it over the ocean. And so they're doing the same sort of a thing. So that's sort of cool. I'm taking up Colin's time. So other inelastic processes are Brillouin scattering. Brillouin scattering is the light comes in and inelastically scatters off sound waves in the water. And so that's a very, the shift in that is only at 530 nanometers, The shift is only 7 times 10 to the minus 3 nanometers, so it's not a very big spectral shift. But the shift depends on the speed of sound and the index of refraction, which then depends on the salinity and temperature. But the sound speed shift changes more rapidly with temperature. So by measuring this Brillouin shift, you should be able to get a measure of the temperature of the water. So do I have, I don't have it written here. There was a group, Ed Fry, my advisor later on, was working with trying to use this with a LiDAR system to get temperature profiles in the water column. His student, or his, not a student, his postdoc, Thomas Walter, was working with him, and Thomas brought the system back to Germany, and they've been trying to work on it from helicopters, last I knew, to try to get a remotely sensed temperature profile from looking at this Brillouin shift. You can see at 10 to the minus 3 nanometer shift, you got to have really good lasers, and you got to be able to measure these very, very small shifts. Okay, fluorescence. The difference, fluorescence is typically isotropically emitted versus the Raman had the Rayleigh scattering function roughly. We actually did an experiment to make sure it was isotropically emitted, and it is, probably because it's such a longer process. The photons, everything's lost track of which way it came in. So when it goes out, it goes off in all its directions. Longer process. Other fluorescence. Are you going to talk about CDOM fluorescence?
Yeah.
Okay. Well, I won't say other than it's there. Oil. Well, here's oils. She already talked about this, so I don't need to talk about it. This is an important thing because CDOM fluorescence, in generally, people ignore it, mostly because the emission's happening in the blue and where there's already a lot of light, so it's not going to affect things too much. Now, to include that in a radiative transfer code, you have to have the quantum fluorescence efficiencies. Okay, telling you how much for this excitation, how much goes into some other wavelength. That's the only way you're going to be able to do it with a model. The only measurement I know of that for CDOM is Haas et al. And that, I think you have a switch. You can turn it on in Hydrolite.
We did that in this class.
What's that?
Steve Haas did
Yeah.
that experiment as his project.
Oh, really? In this class?
Yeah, he's Ken Carter's student.
Well, okay, if you talk to, or the chemists I talk, chemical oceanographers I talk to, say that the way he did it probably has very little to do with CDOM fluorescence in the natural world because of the processing steps he had to go through to concentrate all of the CDOM.
He concentrated like 400 liters of water and then extracted it out of it.
And then extracted it
Yeah,
with,
there's a lot of solvents.
yeah. So if you talk to the people Ellie Zika and people I knew who were really into CDOM fluorescence and such, the chemists, the processing he did probably changed completely what the quantum fluorescence efficiencies were. So when you go into Hydrolite and turn on that switch to use it, take it with a grain of salt because it's probably not realistic for the real world. So.
It's rather interesting that this whole business of when you include xenon fluorescence and hydrolite all rests on this guy's master's thesis in 1992. And after he got it, I guess he said, I've had enough. He went off and joined a jazz band and has never been heard from since. At any rate, everybody uses fluorescence excitation and emission spectra, but they only get relative numbers. You know, they're interested in the pattern, and that can be used to identify what's in water. They really hard. This guy measured the absolute numbers that I need in hydrolite. So I don't know how good or bad they are. It's really kind of strange that nobody's has improved on that I know of.
Yeah.
But I think part of the problem is these spectrophotometers, you have to do corrections on the excitation to make sure you have the same number of photons coming out of every wavelength that are impingent on your sample, and then your sample absorbs it, and then it refluoresces it. And then you have to make sure that the detector that is detecting the fluorescent energy has uniform response across the emission. And those are really complicated corrections to make. I had a student do it, and it took, and particularly for CDOM, which has this huge range of excitation and emission, there's no one compound that you can use as a quantum corrector in the instrument. And so, people haven't really done it. And then, you have to be able to not only do that, you also have to be a good chemist, and you have to be a good modeler. So it takes a village.
So
It's not
yeah.
straightforward. We'll talk about it a little bit in lab. Yeah.
Yeah, so most people, like Kurt said, basically relate it to quinine sulfate or some other standard. And so I went to an AGU meeting a few years ago and wandered into the CDOM community to see if they've changed anything in 20 years. But no, they're still doing these relative measurements. And that's what I wanted to try with this instrument, is if you put polarizers in there and knew the Raman peak, then you could maybe calibrate with the Raman peak and get an absolute measurement.
That's a really clever way to do it, because water is like perfect,
And,
perfect standard.
right, and if you know the polarization state for sure, then you can calculate the cross section real easy.
Quinine sulfate is just only, you have to make a perfect solution. How do you check it in your absorption?
Yeah.
Spectrophotometer, and then it's only useful over a limited range.
Yeah. So anyways, that's would be interesting to do. Other things, oils fluoresce. Not very useful in terms of natural light field. Very useful if you have an oil spill and you're trying to fingerprint it. Minerals. What's that?
With Horizon,
Deep water horizon. This.
Because Horizon can generate a lot of job for a lot of people that were into these fluorescents.
Yeah. So probably the first time I showed this, it wasn't very important. It became very important very quickly for a limited amount of time. Yeah. And then minerals fluoresce. They're really cool. Unfortunately, they fluoresce usually like the 365 excitation, 320, 254 excitation. Not really very much light in what we're dealing with, but pretty cool pictures. So inelastic scattering, Raman's important to take into consideration when you're modeling light field, especially if you're working in the red wavelengths. Brillouin scattering, interesting to use. As I say there, Thomas Walter last I knew, was playing with it in Germany to try to apply it to the field. Trying to get a laser that was, very low noise laser to work from a helicopter was tough. CDOM fluorescence, important for measuring CDOM. Not as big a deal in the natural light field, and at least what I've seen in my data. I've even gone to places like Shark River that had a whole bunch of CDOM and couldn't really see the fluorescent signal. And you could read the rest. Oil fluorescence, mineral fluorescence. Okay? So that's inelastic light field with a few of my opinions thrown in. Any other questions? Yeah.
Silly question. So
No,
is fluorescence truly inelastic scattering, or is it something else?
You can think of it as if you'd like, you could call it inelastic scattering, because it's a process. The photon comes in and comes off with a different wavelength. You could call it that if you'd like. The difference,
Absorption.
but it's
It's different from the inelastic scattering like Raman, because it's actually absorbed into the molecule, and then there's heat loss, and that's what leads to the re-emission. So,
well,
I think you could call it inelastic
that energy went somewhere in the molecule. An inelastic Raman scattering, that energy got stuck in that molecule in water.
Does it warm it up?
It's gone somewhere. It must have warmed it up, yeah. Or cooled it off if it's the anti-stokes. Took some of the energy away from it.
Right, right.
So it's still, it's that process. I think it's distinguished as much, if you want to, by lifetime.
Right.
And lifetime and using these virtual states would be another thing.
The scattering distribution too, right?
Fluorescence tends, because of the lifetime, fluorescence tends to be, will be isotropically emitted, and the polarization, it's not polarized when it comes off. Yeah.
So for fluorescence, are you also passing through that virtual state, or are you going to an excited?
Fluorescence, you're using a real state in the molecule.
Okay, so it's an excited state.
Yeah.
Yeah.
When you're dealing with lab systems where you have higher concentrations of chlorophyll and like not pure water, not seawater, should you be concerned about the Raman scattering?
So in the natural light field with chlorophyll, with all the other things, if you look in the red wavelengths, you will see Raman scattering. These are real. This is a real measurements of the upwelling radiance attenuation, and this is pure water. So all of this part of it is occurring because of Raman scattering. So you're seeing this in the light field. There's a lot more red light than there should be. Notice this big dip. What's this big dip? So this is a diffuse attenuation, and I'm getting a big dip here. Chlorophyll what? Chlorophyll A what? Fluorescence. So this is the fluorescence, chlorophyll fluorescence. So you're getting a combination here of Raman and then also the chlorophyll fluorescence peak, depressing what I measure as a attenuation. So it occurs in the red wavelengths above. Anywhere above, my rule of thumb in clear water is 575 nanometers. Above 575 nanometers, you really have to start worrying about it. Yeah, so I'll leave it there for right now. Anything else? Okay, all right, good. What time do you want to start, Colin?